Hi guys, today we are going to discuss about an interesting data structure, trie. Trie is majorly used in word searching. So today we are going to understand what is trie, what is the internal composition of trie, what operations we can do on trie. So basically, trie is a tree that stores strings. The maximum number of children of a node is equal to the size of the alphabet. Now, what is the meaning of that? So we are going to understand it. So each node, instead of storing a string, it actually stores an alphabet or a character in it. And it has the entire collection of characters which are linked to their respective nodes. So to understand this, first we need to understand the composition of trie. So let's go and try it. So let's say if you are creating a class called try node, so it has two properties in it. First is the child, which is actually a map uh, of characters, and each character is pointing to its individual try node. Let's call it child. And another one is a boolean, which is end of word. So this is the composition. Now each node has both of these properties. So generally the end of the word is false. Then we have this map in between. And then we have further nodes which are connected to each other. So let's say if we wanted to create a trie for A, B, C, D, E, this is the first word. Now what we do from the root node, this let's say this is the root. From root node, we search the first character, which is A. We check that whether A is available in the child map or not. If it is not uh, available, then we insert that A node into the map and we create another node and we point this to this. So this is how the composition is. So this is what this map is doing over here. So it has key as characters and the value is the trie node. So this is what we are doing here. Uh, the first character A of this word is inserted into this map, and then we created a new node and we pointed to it, and the end of word is false. Now we look for this second character, which is B. B is not available in the second node, then we insert B and we create another node and we put similarly like that. And then we do it for C, we do it for D, and we do it for E. So we put insert C, which is pointing to another node, F. Then we insert D, which is pointing to another node, which is E. And then E is pointing to a blank node. Now we have to be very careful here that this is the end of the word. So we mark this node end of the word flag as true because this signifies that okay, this is the entire complete word and this is the last node. Similarly, if you wanted to insert LMN, so L is not available here, so we add enter L, then we point to another node, then we insert M, which point to another node, then we insert N, which points to another node, and we mark it as true. Now let's say we wanted to insert a similar word, A, B, C, D. Now we search in this first node whether uh, character A is available or not. Yes, character A is available. Then we look for the uh, linked node in the map for that character. Yes, that node is available. Then we check for second alphabet, which is B. B is also available. Similarly, C is also available and D is also available. Now, A, B, C, D is the complete word. So we change this flag from F to true, which signifies that, okay, this word is completed over there. And I'll explain the significance of this flag when we are doing a search or delete. Similarly, if we add PQRS, so P is not available, so I'll add P here, then Q goes here. Again, it's point to another node, again it points to another node, and this points to a blank node. And similarly LMQRS. So L already there, M already there, but there is no Q in this one. So we create insert Q, and Q points to another node, which is R, and then it will point to another node, which is S. Okay. Okay. So till now we understood how we are inserting words in a trie. Now, after inserting trie, we got the entire data structure with us. Now, how can we do search into that? So, for example, we are going to search A, B, C, D in this trie. So, how we are going to do? So, similarly, the way we inserted it, we will start searching the same, searching character by character in the trie. So, we'll start from first character, which is A, and we start from root. So A is the part of this entire uh, map, or the child of this node, and we do have A here. So okay, that character is found, then it will return the try node, which is linked to that specific character. Now we will look for B in this try node, which has been returned, and we found that okay, B is also there. Then it returns C. Then we will look for C, and we found C also in the node's child. And then we'll look for, similarly, look for D and look for E. And then whatever node is connected to E, we found that there is another node, and the flag should be true, which signifies that this is the end of the word, which is inserted, and the the method which is searching it will return true, stating that yes, we found the word. Similarly, if we look for A, B, C, so we do have A in the root, we do have B in the child node, and then we do have C. But the node linked to C is not marked as true. So it means that it's not a complete word, and this search will fail and it will return false. This one will be true. Similarly, if we do for LMQR, L is available in the uh, root, and M is also available in the node linked to L, and then similarly Q is available, and then R is available. But again, the node which is at the end of R is not the end node of that word. It's not marked as true, so again this will be a false. It's a false search. And in case of PQRS, P is available in the root node, then Q linked to it, then R linked to it, then S linked to it, and it has a last node linked to it, which is marked as true. So it's a complete search, and for word is found, so it will be marked as true. So this is the way we search words in a trie data structure. Okay, so till now we discussed about insertion and search in a trie data structure. Now we'll discuss about deleting. So deleting is a bit tricky. So how do we do that? To delete, let's say, for example, if we are going to delete A, B, C, D, this word, then we traverse in the same way. But at the end, how we are going to remove nodes, it depends on different scenarios. So for example, for A, B, C, D, we traverse from root, we found A, then we found B, then we found C, and then we found D. Similarly, we are going to traverse. But we cannot just remove all the nodes A, B, C, D, because B is pointing to E, is another uh, word been stored here. But we can see that the next node has end of word as true, which we will mark as false, because we are now the A, B, C, D is not the part of the words in the trie data structure, so we'll mark it as false. So when next time we'll search for it, we don't find a true at the end of the word, then this word will not be searched. Now, For the second one, where we are going to delete A, B, C, D, E, again, we'll start from the root. We'll search for A, then we'll search for B, then we'll search for C, then we'll search for D, and then we'll find E, and we found the last node here. So what we will do, we will delete this node and we'll remove E from this map. So this will also be removed, so it will become blank. And similarly, when we'll move back, then we'll see that, okay, uh, D is the, okay, so why we remove E? So here in this map, we have E as the only key. So we'll just remove that E. If it could be possible that there are other keys in it, like, F, G, H, which have their own nodes linked to each other. So in that case, we don't just remove this entire node, or we just clean off E. So now D is linked to E. If the entire map of child is blank, then we do the same thing here. We will remove D, and then we'll traverse back to the top. And if again this is also blank, then we will remove C, and similarly we'll remove B, and then we'll just remove A from the map. Now see, we cannot remove the entire root node because there are L and P available, which are for other words. So this is how we remove uh, the word from a tree if the entire word is found and all the nodes don't have any linked words. Similarly, we look for LMQR. L is here, M is here, then we have Q, then we have R. So again, in this case, this is not a word at all because R is not the because the node which is linked to R is not marked as T. So this word actually do not exist in the tree at all. So there's no need to remove it. It's already removed or it's not existing. PQRS, we look for Q, P, Q, R, and S. Okay. So in this node, the end node is blank and it has T in it, which signifies that this is the end of the word. So we'll remove this node, we'll remove S from it. Then we'll traverse back to R and we said, okay, the node which R linked to, it's also blank, then remove it. Then remove this and so on and remove P. Similarly, this is the way we delete words. Okay, now we jump on to the code, how we are going to code all of these three scenarios. So this is the structure of try. Now we are going to write the method for try. So I'm using Java uh, for this use case. So let's start it. So first we need to construct the properties for try. And constructor, we are going to initialize these. So it's going to be false. Okay. Now, first we need to insert it, then we'll try some of these test cases which I have written here. So let's write insert. Okay. Okay, so the method is really simple. So as we know that this is a nested data structure, so every character has its own tree, then that try has its own character and they just have their own try, so it's going on in and in. So what this line is doing, this code is doing, it's getting the current object of the try, and then according to the size of the word we are looping over the entire try, and we are searching character by character. So we can find the first character at 0th place, and then we'll see whether the character is available in the map or in the tries child or not. If it is available, then we just set the current to the that child node, And if it is not available, then we create a new node using the try constructor, and we set the character in that node, and then we set the current nodes to that node. Similarly, we'll write the search method. It's mostly going to be same, so let's just copy paste it. And if it is not found, then we'll return false. This is going to be true. So similarly, we set the current to the current context, which is this, and then we'll start searching for each character by character. Uh, if it contains, so this is not going to be, yeah. So we'll start searching character by character. Uh, so we'll start searching character by character, and uh, the first character, it will search whether that character available in the map or not. If it is available, then it goes to the linked node, and so on and so on. And at the end, we are returning the end of the word. It could be possible that it's a false end of the word, so it might not be the actual word which is inserted. It could be a middle of the word. So in that case, that flag will be false. So accordingly, we will return the flag, and this return, if we don't find the word, then in the middle, if the character is not available, then it will return false in that case. So we'll do a quick test for these two methods, insert and search, then we'll work on the delete method. Um, so first we are inserting apple, then we'll search for apple, then we'll search for app is not available, then we will insert app, and then we'll search for app, or let's say we just do one at a time. Okay, true. So we inserted apple, then apple is found. Then let's try to search for app. Yeah. So we did inserted apple, but we did inserted app as per apple, but app is not the complete word which is inserted. Apple is the complete word which was inserted. So when we try to search it, it returns false. Now we are going to insert app, and then we will search for it. In this case, yes. So initially we did not inserted app, that's why it returned false. Then after that we inserted app, and then we try to search it again, then it returned true. Okay. Now we will work on the delete method. Okay, basically, so we are doing a recursive method here. So we are checking a base case. The base case is that once the index is same as the word's length, in that case we are checking uh, whether this last node, this last node at the bottom, is the end of the node or not. If it is end of the node, then we just return false, and we are done. Uh, and if it is not, then we'll set it as false, and we'll check whether that node has any other child characters in it or not. Accordingly, we'll return true or false. Now this is the simple case. We are extracting the character at that index. Then we are finding the that node in the map, and if it is not available, it means that it's the end of the word, and we just return false. And if it is available, then we recursively run the method till the end of the word, till the last character, which is going into this base case. Uh, Once it returns back in the recursion, then we'll see whether this delete node is returned as true or false. Accordingly, we'll just keep removing all the children's, and we'll keep checking each and every node after removing that children from that node, whether the size of the node is 0 or not. And if it is true, then we'll return true. If it is false, then we'll return false. If this node is not deletable, then we just return false. This way we are deleting it. So let's quickly test it out. Let's delete apple. Oops. Should be double characters. Then we'll search for apple. See, we found apple initially, and then we deleted it, and then it is saying false. So this way the word got removed. Okay, so now I'm going to add an additional function to this data structure. We are going to find all the words in the trie data structure which starts from some specific prefix. Okay, so okay, so uh, the concept is similar as we have in other search method, that will search each and every character starting from the character at the 0th index, and if we found all the characters in between, then we'll just return true at the end. If one of the character is not found, then we'll return false. Removed, so let's run this thing. So we found starting with ap at the last, and we try to search for any word starting with prefix d. That's we don't found. Now the complexity, uh, as we can see from this data structure, the complexity is big O of L, where L is the length of the word. So there are only 26 characters in English. So each node max can have 26 character long map in it. And while insertion or search, we just only need uh, like the number of operations will be done equal to the length of that string. So that's why the complexity is big O of L. Thanks for watching this video. Please like it and subscribe my channel for more videos like this. And if you want something specific to be discussed about, let me know. I'll create videos on those topics also. Thank you.